Next, in our description of magnetism, we wish to look at the sources of the magnetic field. This will begin chapter 28. In the last chapter, we looked at the forces that resulted from a particle moving in a magnetic field. So let's review that very quickly and see what that led to. So this is going to be chapter 28 in the first module, which is going to be on the Biot-Savart law. But for our quick review, we looked at forces. And we have electrical force, force electric. And the electric force is the charge times the electric field that charge finds itself in. And we had a force magnetic. And the magnetic force is Q V cross B, where we have the cross product of the two. And there's an equivalent way to look at this that we derived that looks at currents. And this would be the current that flows times a length. This is for an infinitesimal force, dr, or let's say dl cross b. And this is where a current I flows in a little segment of length dl, and the direction is given by that, in a magnetic field, and gives the force that's due to a current. These are the same equation, one for a charge and one for the current. Now, in terms of where do we get the fields, that's done by a separate equation. You'll recall that charges, if I think of the charges here, charges will create a field, both magnetic and electric, and the electric and the magnetic field exert forces on other charges. So we have this reciprocal part where we first have to say, given the field, what are the forces? And that's done by these two equations. We just finished the chapter on these two equations here. Now we need to know how these fields are generated. Well, how does the electric field come about? The electric field comes about, and you remember this issues from taking the force, which is the Coulomb force, and dividing by a charge, as Q divided by R squared. And this has a unit vector associated with it pointing away from this charge. I won't go into that again. That gives the vector nature of this, but a little unit vector R. And therefore, if I have a charge Q, the electric field flows outward from that and a distance R away. The charge is given by KQ divided by the square of that distance. K here is given by 1 over 4 pi epsilon naught. And for practices of our course, we're going to approximate this by 9 times 10 to the 9th. And this K value can be approximated by this very, very closely to about 1 part in less than 100, less than 1%. So now what we want is, how do we get the magnetic field? Well, the magnetic field comes from the motion of charged particles, or currents. So what is this equation? Well, that will take us to the Biot-Savart law. Biot-Savart law says that the infinitesimal magnetic field is going to be mu naught over 4 pi epsilon naught, 4 pi, and that's the constant. You remember up here the constant K was what? K was 1 over 4 pi epsilon naught. Here we have a 1 over 4 pi, just as before. But it turns out that everywhere in electricity we have a 1 over epsilon naught. We now have a mu naught in its place. So they invert places, and this we'll discuss in just a second. Times a current, let's see, that's a capital I, times in a small segment, ds or dl, crossed with an R unit vector, a distance R squared away. Now, what does that mean? Well, that means that if I have an infinitesimal little segment here, ds, and it's handling a current I that's flowing in it, it's of length ds, which is infinitesimal, and the length points in the direction of the current, then if I go away a distance, R squared, and look at the magnetic field that would arise from that, it will be mu naught over 4 pi times the current times the amount of length divided by the distance squared. And you'll notice that this is a cross product. And that cross product is a cross product of ds, which goes in this direction, and a d unit vector, which goes along in the direction where we want to know the magnetic field. What's our magnetic field, infinitesimal magnetic field at this point? Well, it's going to be a cross product of those two. So it's ds cross the unit vector r, and ds cross r comes out of the board. So this is out of the paper. And so this magnetic field is going to come around and circulate about this little segment. So you can imagine this magnetic field is coming straight up, going in a loop, and we'll try to draw that loop now, like this. And the magnetic field comes up out of the paper. Over here it would dive back into the paper, go around in a full loop. And it's going to be given by the sine of the angle between these two, which means that as I go very far forward, so where my ds is like this and my magnetic field is here, where this is a small angle theta, it's going to depend upon the sine of this angle, which means this gets extremely small, so there's almost no magnetic field in the front and the back direction. But the magnetic field is a maximum in the perpendicular direction, where the sine of the angle becomes 1. Now this value, mu naught over 4 pi, is exactly 1 e to the minus 7th. That's the way the SI, or Scientific International Units, are set up. So this constant, you must remember, is 1 e to the minus 7th. And that's called the permeability of free space for mu naught. Mu naught is a permeability of free space. So that, divided by 4 pi, is in our unit system that we're using exactly this value. This is sometimes called K magnetic, which is the mu naught over 4 pi. Now, knowing that, it's easy to calculate mu naught. It's going to be 4 pi times e to the minus 7th. Unit vector r points toward the little segment out here where it is located. And we could compute this for a simple problem. And our simple problem that we're going to work on is we're going to take a current of 4 amps in a segment of 2 meters, go out 30 degrees, a distance of 3 meters, and say, what is the magnetic field at this point? And the answer is the magnetic field, I write it as an infinitesimal here, but I could write it as just the magnetic field, is going to be equal to 1 e to the minus 7th, that's the constant in front, exactly like our 1 over 4 pi epsilon naught. Now remember, that number was not exact, but this one is absolutely flawlessly exact. Times our current is 4 amps, times our infinitesimal length. It's 2 meters long, not quite infinitesimal, but good enough. It's a little straight wire. And I have to divide by the distance squared. Well, I'm 3 meters away, so that's going to be 3 meters squared for the distance. And now I have to add into that the sine of the angle between them. So this is the sine of 30 degrees. And that comes from the fact that that is the angle between the unit vector r hat, and the length dl. And now we'll say, okay, this gives us the magnitude, and you may recall that sine 30 is equal to 1/2, so this is going to be, we can solve this in our head. Since the sine of 30 degrees is 1/2, this is going to be 4 times 2 is 8 over 9, so this would be 8 over 9 e to the minus 7th. You can work out that ratio on your calculator. And that would be in Teslas. Remember, the Tesla is the unit for the magnetic field. Now, what is the direction? That would be the next question. And the answer is, to that, you'll notice that this cross product is ds cross r unit vector. That's this vector cross this one. Well, that would say use the right-hand rule, grab the perpendicular to the plane of the two vectors, and that would point upward. So this is out of the paper. Out of the paper. Straight out. So it points directly towards your face from what you have computed. So this is this, and it's in the outward direction. So now we understand how a magnetic field is created by a small piece of current segment.